Hi, my name is Kurt, and I'm the manager of the MBE lab here at UC Santa Barbara. We wish you could be here with us today. It's a beautiful day, 72 and sunny in February, but unfortunately you can't be. So we're going to do a virtual lab tour. It's the next best thing, so follow me. So the question you might have is, what is MBE? Well, MBE stands for Molecular Beam Epitaxy, and the dumbed down version of what we do here is spray painting with atoms. But you've all been accepted to the graduate program here in the materials department, so I can do a little bit better than that. Got our brand new dual chamber MBE here that I can demonstrate on. So what happens in an MBE growth chamber is we have material sources here. These generally get heated up and form a molecular beam which travels from the material source to a substrate you can just imagine is right here. Once those beams arrive, we have very carefully controlled temperatures, and we do lots of monitoring to make sure that we form really nice, perfect crystals of various different materials. We then use characterization techniques that happen during growth to actually observe the film growing layer by layer. And you can observe each atomic layer growing. The MBE crystal growth technique works for a variety of different material systems, so the MBE lab has grown quite large since it was founded in the 80s by one of UCSB's Nobel laureates, Professor Herb Kromer. For a more in-depth look at what we do here, we're going to talk to several of our graduate student researchers, and they're going to show you the equipment they work on and the research that they do. Let's go to them now.
Hi, my name is Clayton. So this is the nitride MBE, and so what we grow is basically the stuff that makes LEDs, all the different alloys of these systems, so the gallium nitride, indium nitride, aluminum nitride, and the alloys between these guys. What's so special about this guy? Well, besides having the standard fusion cells, we have a valved magnesium cell that instead of controlling the flux of the dopant using the temperature, we would control it using the opening of the valve. And if you move over here, we have a cryo panel in the, which is a manifold in the MBE system. And what that does is that it cools down the material system, the system, and condenses ammonia ice onto it, and therefore that reduces the overall pressure of the system. That guy over there is a big old turbo pump. It's probably one of the biggest turbo pumps in the MBE lab. That's probably a 10-inch flange. And right over here is our ammonia bottle, which supplies the ammonia into our system. The ammonia part supplies the nitrogen part of the nitride material system. And my research is basically geared towards understanding all these material systems and how they work at the fundamental level.
Hi, my name is Christian Worm. I'm a fourth-year PhD student in the electrical engineering department here at UCSB. The system you see in front of you is a nitride variant Gen 2 plasma-based MBE system. Unlike the system you see next door, which uses ammonia, this uses nitrogen gas, which is activated via an RF plasma source. We have two plasma sources. One is for high flux growth, one is for standard growth rate. We have conventional gallium, indium, and aluminum fusion cells for growing, algan, aluminum gallium nitride, indium aluminum nitride, gallium nitride, and indium nitride. And the reason you see this system is all boxed up right now is we're actually running a bake. So every time we do maintenance on a system, we open it up and expose to atmosphere. Water molecules tend to get inside the chamber and coat the walls of the chamber. By covering the system up in this big bake box you see right here, and then heating up to about 100 degrees Celsius, we can vaporize any water that's accumulated on the surface, which gets expelled through our two different cryo pumps that we have here. So this system in particular has been mainly used in the past for growing high electron mobility transistors, or HEMTs, used for millimeter wave communication. The early work in our group done for nitrogen polar HEMTs was all done on this machine, all of our early proof of concept devices. In addition to that, this is also utilized for growing tunnel junctions for light emitting diodes, LEDs.
Hi, my name is Nick Combs. I'm in the Stimmer group. I work on oxide systems. We are here in the main lab where we have 4 systems, 2 of which are our oxide systems, the old oxide and the new oxide. We also have a 3.5 system called System C, which is more of a shared system. And then we in the Stimmer group also have a dual chamber system here in the back that one of the chambers is used for cadmium arsenide and the other we're still figuring out. But I'll talk about oxides. So we have here, we have the new oxide 930. It is a Veeco Gen 930 MBE chamber. So like most MBE chambers, we have our fusion cells up front. So we have our traditional fusion cells right here. This is an oxide system, so we also have an oxygen source, which we also have a plasma source attached to in case we want to increase the activity of our oxygen to help oxidize some things. And then some of the bread and butter of the Stimmer group, we also use metal organic sources. So these are metal organic gases, which we thermally evaporate through these tubes. And by using these, we can grow with materials that are not traditionally able to be grown through a fusion cells. These allow us to use other elements, but most traditional MBE uses what's known as an effusion cell, which you put your elemental sources in, and then you heat that up, and then the molecular beam is what comes from that. And I'll show you that right now. So right here, we have one of our effusion cells. This is the back of what you saw at the front of the chamber. And so this is what goes inside of the chamber. And in here you put a little crucible, fill it with source material, and load it on your chamber. And that's how you grow. You have little resistive heaters in here, which is what heats up your source, and you have a thermocouple, which is PID controlled by Eurotherm. So this is what most MB sources will look like if it's not a gas source.
Our group focuses on growing cadmium arsenide, a 3D direct metal by MBE, and this is our system. And so this MBE system really embodies the long tradition of MBE here at UC Santa Barbara. And so this one was originally intended for the growth of high mobility semiconductors, which date back to the 80s and 90s. And now we use these generations of knowledge and experience towards growing new materials, these new topological direct semimetals, which is a very exciting area of current research interest. And so, like all the other MBE systems, it mostly consists of several interconnected vacuum chambers, a substrate heater, and fusion cells, and characterization equipment.
So one unique thing about the cadmium arsenide system is that our cadmium arsenide sources here and here are retractable cells, meaning that we can move the cell backwards and then close off a gate valve here to isolate the cell from the main growth chamber. And the advantage of this is that we are able to refill our cadmium arsenide source material without having to vent the entire MBE. That means that we can refill source material in a day, whereas for the non-retractable sources such as aluminum, antimony, we would have to break vacuum on the entire system, replace it, and then do a bake out, which would put us down for at least a week.
So the challenge is really growing your material at the right temperature, finding the right substrate for your material, delivering the atomic fluxes in the right amounts. And so given these challenges, our group has actually succeeded in demonstrating the first growth of cadmium arsenide by MBE. And over the past 5 years, we have actually published 20 papers related to the growth of cadmium arsenide on this system. And so if you want to learn more about this system, please check out our website and the links that we post.
Thanks for virtually stopping by our lab. UCSB has so much to offer, from world-renowned faculty to world-class facilities, a wonderful town, and a great natural environment to spend your time in. You've probably seen enough videos of the beach, so I won't take you there now, but hope to see you in the fall.